I made it. Wow, what was that all about? We're talking today about risk analysis. And actually, risk analysis is really very simple, but it is so botched up in the newspapers that we're going to have to spend some time deciphering what's going on. I hope you understand it because it is important to us. Pure risk. Think of Russian roulette. In Russian roulette, what happens is, as we saw, there's a pistol, and in the pistol is one shot. There were 8 slugs in here. I shot 7, and then I spun the dial so that I didn't know which was next, and I shot it. And I was lucky. Had that been the one, someone else would have had to complete the lecture. However, I made it this time. I was at risk. However, there was 1 slug left and 8 cylinders. And since I spun it, the 8 cylinders were random. Each one had an equal opportunity of being next in line. And therefore, I had a 1/8 risk, which is 12.5%. I had a risk of 12.5% of getting my brain shot out. Okay? That's pure risk. No problem. Easy to figure out. We have absolutely no trouble understanding this. Every one of us will understand that if there are 8 positions, one of them has a shell in it, there's a 12.5% risk of getting shot. Well, frequently we don't have this information available. What we have is data. And then we get what's called assessed pure risk, an assessed risk. Let's say we have a roulette club. And in our club, there are 100 members. So we started this week. Last week, there were 100 members. We have another meeting today, and only 88 members show up. Well, each member was told to go home and play Russian roulette, and they played Russian roulette. And only 88 members came back. And the other 12, well, we attended their funeral during the week. All right, this morning. This morning we attended their funeral early, and then we came to a meeting. Well, now how do we assess the risk? The assessed risk is 12%, because 12 people out of 100 got shot. 12 out of 100 got shot, therefore we figure there's a 12% chance when you play this game you're going to get shot. If we didn't know how many shells were in the gun, what chance there was of being shot, we play the game and we find out 12 people got shot. Out of 100, 12% risk. Everyone has a 12% risk. Well, if these 88 people go back and do it again next week, 12% of them won't come the following week, or approximately. For pure risk assessment, which is what we're talking about, the sample universe must be proper. Now, I say this, and I'm going to talk now about how things aren't what they appear. We have to protect ourselves at all times of people who are misusing or not understanding, not using statistics correctly. They're trying, but they really don't understand it. We're trying to see through what they're doing. And so I say that for pure risk assessment, beware, because you must have a proper sample universe. Let's do the following. Let's look at an example of an improper universe. Let's take our roulette club. There are 100 people in the club, okay? Now the 100 people go home, and next day, today, they meet again, and there were 97 people there. Well, the assessed risk is 3%. Only 3 people died in 100 members of our club. Well, that's nice, but this 3% doesn't mean anything at all. This is just a worthless number. Because what if the universe was such that only 24 of the original members were active? That is, 24 people played the game. The other 76, they just came for the hors d'oeuvres. Well, 24 played the game. Of that 24, 3 didn't make it. 3 out of 24 is 1/8. 1/8 is 12.5%. So the active group, if you're active, your risk is 12.5%. You're at a 12.5% risk of getting killed if you are active. If you're inactive, there's no chance of being killed. You don't have a gun. How are you going to shoot yourself? If you're inactive, there is no chance of your shooting yourself. If you are active, there's a 12.5%. Yet the report was 3%. That 3% had no meaning whatsoever because the universe was not proper. It wasn't. The universe should have been 24 people, not 100 people. Okay? Let's try another one. Incompatible data. Another problem that occurs in assessing risk is incompatible data. This occurs very, very often. Let's say there are two cities. City A boasts a crime rate of 10%. So if you move into this town, the risk of being assaulted in a year is 10%. City B says they have a 20% risk of a crime. So if you move this in, you have a 20% risk of suffering a crime in this city. Well, which city should I move to? I have to move to a city. Should I move to A? Should I move to B? Assuming that crime is important to me. I want to avoid it as much as possible. This is a 20%. This says 10%. Which should I go to? Well, it turns out that City A, that's New York City. And the definition of a crime there is a crime only if someone is caught and convicted. So if the criminal is caught and convicted, then it's considered a crime. Otherwise, no crime. Well, they use the philosophy, you're innocent until proven guilty. So unless you're convicted of the crime, there's been no crime. City B is Blacksburg. Now, if Mrs. Smith calls the Blacksburg police and says, "That college boy is parked in front of my house and he's visiting his girlfriend down the block. Please come and tell him to move his car." The police come and they report it. They say, "Oh, a crime has been committed," because the definition of a crime is anything reported. So if someone phones in and says something's not right, they report that as a crime. Okay? Two definitions of crime. They're not the same. City A, New York City, 10 million people. 1 million people were convicted of a crime this year. 1 million people convicted of a crime. There's only a 10% risk of a crime in New York City. Blacksburg, there were 10,000 people, but there were 2,000 phone, either tickets given or people called up to say someone should move their car or a cat's up in a tree, come get it out. There were 2,000 of these calls. 20% crime rate in Blacksburg. Which, if you're worried about crime, which town should you move to? The one with the lower crime rate. Well, no, because there's incompatible data. The data here and the data there are not the same kind of data. They are not compatible with each other, and you shouldn't be talking about them in the same breath, what people do. The same kind, I've seen that over and over and again. For instance, people talk about child birth or death rate. Infant mortality. United States is the highest of any civilized country. You believe that? I don't. What happens in the United States, if someone goes in to deliver and the child does not come out alive, that's a death, and we have an infant mortality. In another country, a child has to live for a week and then die to be considered infant mortality. Otherwise, it's not counted. It's a death in birth or something like that. You see, if you have different ways of counting what you're counting, all bets are off. It happened when we did unemployment rates. What they did is they had a high unemployment rate, and all of a sudden, the administration reported a low unemployment rate. What happened is nobody got jobs. They changed the definition of employment rate. They changed it. These people are no longer eligible. If you were in school and were only looking for summer jobs, you're no longer counted. So this week it was counted, next week it wasn't counted. The unemployment rate dropped significantly. Different definitions. You can't use different definitions and expect to be able to compare things. Okay? So, incompatible data, I call that. The next problem comes from what I call strange data, and you'll see why. This is accident risk. Okay? In this town, males under 25 are at 90% risk of being in an accident in the next 5 years. Well, what that means is I'm not lending my car to a 25-year-old to drive. 90% risk of being in an accident. Well, How do they get that? But what if the universe, people, male drivers in this town, were that there were 90 good drivers and 10 bad drivers? And the 90 good drivers had a 10% chance of being in an accident in 5 years, and the 10 bad drivers had an 80% chance of being in an accident. So we've got two different kinds, 10% for these people, 80% for these people. The 90% doesn't make any sense even looking at that, 90% doesn't make any sense. But really, knowing what's going on, we realize that if he's a good driver, there's only a 10% risk, and that's okay. If he's a bad driver, it's an 80% risk. Maybe I'll avoid those. But still, where'd 90% come from? Let's look. Let's assess the risk. Let's say 5 years have passed, and there's been 9 accidents by the good drivers. Well, that's consistent with 10%. 9 is 10% of 90. There are 8 accidents. Eight of the bad drivers got into accidents. Well, that's consistent because 10%, 80% of 10 is 8. Well, if you look at how many drivers got into accidents in the 5 years, that's 17 out of 100. 17%, I would assess the risk. The risk is 17% of someone being in an accident in 5 years, if he's 25 years old and male. But that's not what's reported, so where's the 90% come from? I'll tell you where that 90% comes from accidents. Not people getting into an accident, but how many accidents there are. In 5 years, the good people, 9 of them got into 1 accident each for 9 accidents total. But the 8 people that got into bad accidents, they did 2 a year. They had 2 accidents a year approximately. And the total was 81 accidents for these 10 people. These 8 people. 8 people of the 10 got into accidents 2 a year approximately. Okay? 90 accidents out of 100 people, 90% accident rate. So they say the risk of a male driver under 25 is 90%. No, that's got to do with accidents, not drivers. This is accidents. You are a 90% chance of being in an accident, but it doesn't mean there's a 90% risk that a person will have an accident. To show you how silly it is, what if the 8 people were in 101 accidents? Then there'd be 110 accidents for 100 people, and you would report 110% chance that each person under the age of 25 has a chance of being in an accident. Well, now that would be absurd, and you would have recognized that something's wrong. When they say 90%, it's plausible, and so you don't catch it. But had they said 110, you'd say, wait a minute, you mean each person has a 110 chance? So that means everybody must get into an accident, is what you're saying. Must. 100% chance means it's must. But it's not so, because the good drivers had only a small chance of being in an accident. It's a totally, you really don't know what they're saying unless they say the whole thing and tell you and show you what the data is and where it came from. So this data would be understood if they told you what it was and where it came from. Let's take another one. Next one I call mixed universes. Mixed universes. College A says, and they're honest, they're not lying, 73% of their graduates get jobs. The employment rate is 73%. College B says 63% of its graduates get jobs. And they're the similar jobs, the same pay and so on. It's not these are all janitors and these are all congressmen. It's the same kind of job. But that means that College A has a 27% risk of not getting a job. If you go to College A, you're 27% risk. You've got a 27% risk of no job. If you go to B, you got a 37% risk of no job. Where should I go? Okay, I'm deciding which college to go to, and getting a job is important to me. And I look at these and I say, hey, College B is higher risk than College A. I'd better go to College A. There's a better chance of getting a job. Quite clear. Everyone would read that in the newspapers and agree with it. However, we have mixed universes, perhaps, and let's look at it. Maybe you can see red and blue on your screen, I hope. Let's say in College A, there are 2 groups of students, science students and humanities students. There's 900 science students, 100 humanities students, and there's 720 science students get a job for 80% of the science students. 10 of the 100 humanities students get a job, 10%. That's a total of 730 out of 1,000 people, 73% got jobs. No lie, 73% got jobs. 730 people out of 1,000 got jobs. Now remember, there's an 80%, if you're in science, you've got an 80% chance of getting a job. If you're in humanities, you've got a 10% chance of getting a job when you're in College A. Now let's go to College B. College B has science and humanities, but it only has 100 science and it has 900 humanities people. Of the 100 science students, 90 get jobs. 90% of the science majors get jobs. Well, that's better than the 80% from College A. Well, let's look at the humanities students. There were 900. 540 got jobs. That's 60%. If you recall, College A, 80% and 10%. Here we have 90% and 60%. Yet, before we had 73%. And now we have only 63%. If you go into science major, you've got a better chance of getting a job in B than in A. If you go into humanities, you've got a better chance of getting a job in B than in A. No matter what you do, you have a better chance of getting a job in B than in A. Yet the risk, the employment in A looked better than in B. That's because the universes were mixed. You had more than one universe in the college. When you mix universes, this kind of thing can happen. And so you really have to look carefully at what's going on. You really have to look carefully. Okay? Now, I want to end with an experiment here, just to show you where the problem lies. The problem really lies in people not having enough time, or not, when they report these things, they don't want to report the whole story because people aren't going to read the whole story. People want little blurps of words, little things. Aspirin cures heart disease. Oat bran cures cancer. They want very short things. They want students are at risk. They want just blurps. And that's what's causing the problem. The blurb is very deceiving. As we just saw, 63% is really a better school at getting jobs, and 73% is. And that, you say, well, that can't be. You have to look deeper into it to see why. So I'm going to give you a little example to show you what happens. You are a GTA. You've gotten yourself a job as a GTA, and you're in a class, and you want to demonstrate some statistical properties, and you want to show how randomness works, and Law Lodge numbers, and coins that are balanced. So what you do is you take a box of 100 pennies and a box of 100 quarters. They're just regular pennies and regular quarters, perfectly legitimate. And you dump them out on the floor. So here's our experiment. We have 100 pennies and 100 quarters, and we dump them on the floor. Oh, by the way, this is the important part. Just before you start this, a newspaper man walks by and he looks and says, "Oh, I see you're going to do an experiment. Can I come in and watch?" And of course you say, "Well, sure, come on in. I'm proud to have the news people here. I have nothing to hide." And so the newspaper man is sitting watching you do this experiment for your students. Okay? Here's our experiment. We took our 100 pennies and we dumped them. And in the first batch, there were 55 heads among the pennies and 53 heads among the quarters, and you look at them and you say, you see, it's approximately a half, just like I told you. It's not exactly 50, but you wouldn't expect it to be exactly 50. You would expect it to be near 50, and these are legitimate. Sure, there are more pennies than quarters, but that doesn't really mean that pennies are more likely to come up heads than quarters. It just means that they just by accident happen to have 55 against 53. So now I take the tails and I sweep them away. And I take all the heads, the 55 heads, and I put them back in the box. Take the 53 heads and I put them back in the box. Now I dump them out again. And 27 of the pennies are heads, and 18 of the pennies of the quarters are heads. And I say, well, that's approximately half. a little bit more than half here, a little bit, well, actually it's a little less than half here, just about half here, and a bit less than half here, yeah. This is a little on the low side, but gee, there were more than half here, and now there's less than half here. It really doesn't mean anything. There's nothing significant about this, except that this was unusually low. It really doesn't mean that pennies are more likely than quarters to come up heads, even though quite a bit more pennies came up heads than quarters in this round. So you're just saying that's a big statistical fluctuation, but it's statistical fluctuation. I just want you to see how things vary statistically. Let's do it again. So you push the tails away, and you put the pennies back in the box. 27 and 18, the quarters back in the box. Shuffle them, spill them out. Now you get 13 pennies and 10 quarters. Well, it's sort of balancing out again almost. See what's happening? This is a little less than half, this is a little more than half, but that's to be expected. One's short and the other is long, and one's long and the other is short. And it happens, and this is perfectly, you see, this is the way random numbers work, and it's about half all the time. So you put the 13 heads in the box and the 10 heads in the box. You shuck the box and you spill them out again. And the fourth time you get 5 heads in pennies and 6 heads in quarters. And you say, well, see, nothing's remarkable. Well, let's do it one more time. And you do it, and you end up with only one of these is a head, and 2 of these is a head. And you say, no big deal. I would have expected maybe 2 or 3, but no big deal. 1 here and 2 here. And you see the law of large numbers works, and and half is what it is, approximately half all the time. And that's my experiment. I guess it wasn't a very good experiment, but thank you for watching, and that's the end of your lecture. You were the lecture, not me, you. And the newspaper man says, thank you for your lecture. It was very enlightening, and that's fine. You go home. The next day you pick up the newspaper, and you read the headline from this newspaper man has put a headline in. Here's the headline. A recent scientific study shows that quarters are twice as likely as pennies to come heads 5 times in a row. And you read that, and you say, where did he get that? So you go back to what happened. And you say, well, gee, I took the pennies, and I put them back in the box. Yeah, this penny actually did come up heads 5 times in a row. Yeah, these 2 pennies, they came up heads 5 times in a row, didn't they? Yeah, but so what? I mean, what does that got to do with anything? That doesn't mean that quarters are twice as likely as pennies to come up heads 5 times in a row. But it's true to say quarters came up twice as many quarters came up heads 5 times in a row than pennies. And to abbreviate this, his interpretation was that quarters are twice as likely as pennies to come up heads 5 times in a row. And the problem is, he didn't lie. The problem is that's the way it was reported. And then when people read that, they think, oh, a real survey was made, a real scientific study, and quarters are more likely to come up heads than pennies. I mean, that's what it sounds like. But if you look into it, it's not true. You have to look into it deeper. And so they ask the question, can I properly interpret? How can I properly interpret risk analysis without a detailed analysis of how it was done? A legitimate question you might ask. As a student, you'll want to know that. How can I analyze this without doing a detailed analysis? And the answer is very, very simple. You can't. You just can't. You must have a detailed description of what was done in order to make the risk analysis. You cannot go by the numbers they give you. The number they give you is as we saw, in many cases, it can be totally wrong. So you can't do this. You cannot. That's one of the things we can't do in statistics, is figure out the risk just by looking in the newspaper. You have to see what was done and how it was done and figure it out. Now, yeah, if the people knew what they were doing, they could report it properly. Unfortunately, most of the people who report in newspapers really don't know what they're reporting, really don't know statistics very well. They're doing the best they can with what they know, so they misuse it a little bit. And unless you understand, that doesn't mean you can do it either, but at least you understand what they've done and how they've done it, you're going to have trouble interpreting them. And so I conclude with one warning. Beware of people who use statistics. I'm not saying beware of statisticians. I'm not saying beware of people who use statistics correctly. I'm saying beware of people who use statistics because they may be abusing it. And it's up to you to beware. The buyer beware, the reader beware. The one who's being bombarded with statistics nowadays must beware of what they're being bombarded. Now, I hope what you've learned in this semester is not necessarily to go out and be a statistician and do statistics. What I wanted you to do is understand enough of it so that you can see what others are doing and sort of say, yeah, I think what they did makes sense, or, hey, wait a minute, there seems to be a little hole in what they're doing. Maybe that's more wishful thinking than actual statistics. And I hope you can do that with what you've learned. I hope.